In this short video, I'd like to talk about two different types of statistical procedures, statistical tests. One is the t-test, which you've already done for other assignment number 1, and this is described as a group comparison. So in this case, you were describing differences in mean values for men and for women, and you compared heart rate and you compared body temperature. In that same assignment, you were also asked to look at an association between groups. Again, these groups were men and women, but this time you were looking at categorical variables. Instead of a continuous variable for heart rate and for temperature, instead of a continuous variable, you were now using those categorical variables that were created based on norms for heart rate and norms for body temperature. And so one of the important things to note is that here, because you had a continuous variable, you needed to first check to see if your data was normal. Here you have categorical variables, so you don't need to have, you don't need to look at whether that distribution is normal. And they're calling this an association between these two variables that are measured by category. So it's described somewhat differently. So let's look at the assumptions for an independent t-test, because that wasn't included in the previous YouTube video. So one of the first assumptions is that you have a categorical variable with two groups. For a t-test, there can only be two groups. If you have more than two groups, you'll do something called an ANOVA, and you'll be doing an ANOVA in other assignment number 2. And then you also need to have a continuous variable. Your continuous variable needs to meet this criteria for normality. And another interesting assumption is that the variance, variance is a measure of variance is standard deviation. Another measure of variance is the error for the mean, standard error of the mean. Those are different ways to look at variance, but those variances should be sufficiently similar. If they're rarely identical, but you want them to be similar enough to do that t-test. And then the last assumption is that you have independent observations, and that's really a pretty simple concept. It means that for any given variable, each participant or each observation is unique. In that same variable, you can't have a person represented twice for that variable. And these are the results for the independent t-tests. I've kind of changed a little bit what I've highlighted. And I think one of the things that I didn't explain in the other YouTube for this very same analysis was that if you look at the differences, so we had significant differences across men and women for body temperature. And if you look at these, those body temperatures are really quite close to each other. They differ really very little. But also notice that your variance is small. Look at how much smaller that standard deviation is for body temperature than it is for heart rate. You have less standard error of that mean. These are both measures of variance. So that very small amount of variance, that very small amount of error, means that it's easier to detect a difference, a significant difference. Remember when we talked about power, we said if you have less error, you have less static in the background that makes it harder to detect that signal, that meaningful signal that's coming from your data. Okay, so now let's take a look at the assumptions for a chi-square. The first assumption is that these are categorical variables. They can have 2 categories, they can have 8 categories, but they need to be categorical. They can be nominal, such as race, where we don't assume that there's this ordered difference, or they can be ordinal, something like categories of temperature, where you have a category with lower temperatures and a category with higher, so you do have this ordered aspect of these categories. Again, you need to have independent observation. So no participant can be represented in one of those variables more than once. And then this is another assumption that wasn't pointed that I'd like to point out here. And that is, for this crosstabs table where you have the frequencies for rows and the frequencies in cells, you should have at least one expected frequency. So there's expected frequencies and observed frequencies. Here we're talking about expected frequencies. And there should be one, at least one in each one of those cells. And that no more than 20% of these frequencies should be less than 5. And we will look at this assumption again when we do the chi-square analysis. Okay, so now let's do the SPSS analysis for a chi-square. So we go up here, select Analyze. We select Descriptive Statistics because we want to get to a crosstabs. Crosstabs are very useful. Whether or not you use a chi-square, crosstabs can be very helpful. So I already have these in here, so I'll put them back. But we wanted to look at differences across males and females. So we are putting that into the column. And we wanted to look at differences in these temperature categories, because we looked at that earlier with a t-test and found a significant result. So now we want to see what happens for a chi-square. For statistics, the next is to select. As you can see, I have selected that chi-square option, and then that's all we need to do to be able to get that statistics. We also want to go in and look at cells, and the things we want to look at in those cells are what we observed. So what were those observed frequencies across cells? And to assess whether these assumptions were met, it's also helpful to click expected. If you know they're going to be met, you don't have to do that, but we're going to do that here to just see if we are meeting those assumptions. And we will look at those percentages for the columns. And so we can continue with that. And we don't need to worry about any of these other categories, so we're good. It's also important to click this Display Custard Bar Charts category, because those bar charts are really helpful for interpreting results. So let's go ahead, click OK. It's running the crosstabs right now, as you can see by this little sign. I've run them before, but now I'm running them again. So now it's done, and we can go ahead and we're going to move and we have our results here. So there's the results with the cross tabulations, there's the results with the chi-square results, and here is our clustered bar chart. So let's walk through those chi-square results. What you're looking at here is a table, and the way I created this table in the PowerPoint that you're seeing here is that I copied the table, the crosstab table, into Excel, and then I simply copied it back into PowerPoint and added these visual features to it that are standard visual features available in PowerPoint. So let's look at this expected cell count, because remember that was one of the assumptions for using a chi-square, and all those, that's highlighted yellow here. And you can see over here in our chi-square test table that 0 cells had this expected count less than 5. So we totally met that assumption for using a Pearson chi-square to analyze this data. Now, if it had been different, if there had been too many cells with an expected cell count less than 5, the easiest way to address that problem is to simply use the Fisher's exact test. And you can see that that is right up here. And the Fisher's exact test doesn't have that assumption, so that would be an appropriate way to solve that problem. Now, by looking at this chi-square test result, you can see that the results were not significant at the typical p-value of less than 0.05. But it was significant at a p-value of 0.10, which is rarely used in the literature. But I think it is helpful as we interpret the results to know that it was close to significant, and it is not inappropriate to point that out. I think what I'd like to remind you of here is that when we used a t-test to look at the mean temperature in that continuous variable, for temperature, that t-test was significant at less than 0.05. It was 0.024. And that is because t-tests are quite sensitive to finding differences across means, and they're even more sensitive when that standard error of the mean is small, and it was small for that particular test. I think the other thing that's useful to take a look at is the proportion of males and females for these frequencies. We can see because we had the same number, we had the exact same number of males as females. In a way, the percentages and the frequencies operate pretty similarly because there is exactly the same number of males and females. If we didn't have the exact same number of males and females, sometimes we want to pay more attention to this proportion than to the actual frequencies. So it is useful to examine more males than females here, more females than males there, and more females here. And examining those in that clustered bar chart really highlights these differences quite nicely. And here we're looking at counts. I don't think I can stretch this over, but in this bar graph, that you can't see the y-axis, but it says count, so these are frequencies. I did make another bar chart using percentages, using that proportion. And you can see it gives you exactly the same results, really, because you had the same number of males as you did for females. That's pretty rare. It's pretty rare to have the exact same number in each of those two groups. And so for sharing these results, it is typically more enlightening to look at how these proportions are different across those two groups. And so using a bar chart you've made in Excel using the percentages. So notice how easy it is to see. Remember, this temperature category in the middle was for a normal range of temperatures, and it's easy to see that we have most participants falling into this normal range of temperature, which we would expect. But we also had, and notice how I'm describing this as a non-significant tendency, for more males to have body temperatures below normal than above normal. So if we compare males below and males above, we see this difference. Now I could have tested whether that was a significant difference by simply doing a chi-square for those two cells. I'd have to create a new variable and to do that and drop out these participants in the middle. But I didn't test that. So in conclusion here, this explains how powerful chi-squares can be when you have categorical data and you want to look at differences across and want to look at those associations across these two categorical variables. But it also shows you the difference between a t-test and a chi-square test.